what you guys know instead of telling you what you need to know. He did cover this last year. I just don't know the depth that he did it in pandemic times here. And so we'll go through each of my questions up there of 5 things and just see where we're at. We'll do the math that goes with this next. And then my goal is to finish with a lab. Whether we get that probably tomorrow is what we're going to do the lab part for. Do you guys know what a gravitational field is? Any takers on that question? Alex?
I'm pretty sure gravitational field exists on all objects with mass and attracts other objects to that object.
Yeah, good. That is awesome. I don't know if I can reword it word for word. So it's a field. I should put a gravitational field. Which is better. So gravitational field, as we know, is the lowercase g with an arrow on top. So whenever I write lowercase g with an arrow on top, that is gravitational field. Write out the word gravitational field, use a lot of letters, so we can make it shorthand and just put g with an arrow on top. So gravitational field is a field that works on any object with mass, which is really anything. But it's not totally true, though, because it also works on light. Light does not have mass. Gravity acts on that, too. Right, electric fields work on anything that has electric charge. Right, that's what we spent all week looking at last week. So this one is any object with mass. 2, what are the units for the gravitational field strength?
Meters second squared.
No, that's the acceleration due to gravity.
Newton.
Newton's just force. You're getting closer. Very similar to the units for electric fields last week.
Newton over second squared.
Nope. Nope. Newtons per what?
Newton per time.
Nope. Well, yeah, newtons per kilogram. Okay, so the units for gravitational field strength. Okay, so your G value is measured in newtons per kilogram, right? Electric fields were newtons per charge, right? Newtons per coulomb was the units we used last week, and your G or gravitational field is newtons per kilogram, right? So you know, based on other things we talked about in physics, right, that your mass is the same wherever you go in the universe, but your weight changes, which is due to the gravitational field strength wherever you are. Do you know the equation for gravity? So Newton's big equation called the universal law of gravitation. Did you guys do this one last year? Got some head shakes. Okay. So the universal law of gravitation is capital F, which is force, right? And we're going to use capital G this time because it's different than the other G. And that is equal to capital G M1 M2 over R squared. So Newton came up with this equation, and we use it a lot in our class, but without your knowledge of it, because we use the simplified version of mg. And this is the real version that works universally wherever you go in the universe. Did you guys do this last year? Now that you see it? No? Okay. So G is the constant. It's the gravitational constant. And that's equal to 6.67. Now I gotta double check this. My brain just shut off there. Is that right? Yep. Just use the Planck constant. So for the universal constant here for gravity, it's 6.67 times 10 to the negative 11 newtons times meter squared over kilogram squared. So if you do like a side-by-side comparison to Coulomb's constant, you'll see that the setup is generally the same, right? It's newtons times meter squared at the top, but underneath it is divided by the object that it acts on. So in this case here is kilogram squared. The second thing that you should see is that the exponent here is minus 11. So that makes gravity very, very weak as a weak force compared to the electrostatic force that we looked at with Coulomb's law, which is times 10 to the power 9. Right? So this is a billion, and more times weaker. So even so, the Coulomb's law explains why your chair is holding you up, because it's based on the force of attraction of the particles inside the chair and the electrostatic forces there. But the force of gravity between you and the person beside you is not strong enough to suddenly start pulling you together, no matter how much time you give it or how little friction there is between you. Okay? In these equations up here, right, your m's, it's the same as Coulomb's law. So m1 and m2 are the masses of your object. And r is the distance between the others. So R, just have to be careful, because sometimes the R is from, if you're dealing with like 2 people, right? The R is just how far apart the 2 people are apart. We're going to look at questions when R is from like the center of the Earth to a satellite. So sometimes your R value is from the center of mass to between the objects to center of masses. So, but when you're looking at it, whether if you have the Earth and the satellite, so here's Earth and here's a little satellite, you know that the radius of the Earth is pretty big compared to, that's going to be the Earth, the radius of the satellite there. So sometimes when your objects are super big and super small, right? We say R is the distance between the 2 center of masses, but sometimes the distance between the center of mass and the actual outside of the object is not super like big compared to the whole question. So we don't worry about like the center of mass of 2 people, because it's very small usually compared to the distances that things are apart. Right? Satellites are like the size of a school bus, right? So the distance of their center of mass to the outside of the school bus is not very big compared to the distance the school bus is away from the center of the Earth. but the Earth's distance is pretty big. It's a couple million meters, and the satellite's not much farther above the Earth's surface than that. So that's why we have to include it in some of the questions, and you'll see that in a bit. Okay. Do you guys have any questions with that equation? It's just another equation, another force equation. It's the last one of the year, though, so you actually know it's not. Take it back. We saw magnetism field. Okay. We're going to, well, if you take a look at this equation here, the next part here, number 4. So what's the difference between little g when we use it in the equation and big G? Does anybody know what the difference is between little g and big G? Well, then one's a capital, one's lowercase. Right?
Oh, the little g is specifically for Earth, I think, which is 9.8 meters per second squared.
Yep.
Right, whereas the big G is a gravitational constant, so it works for like anywhere in space. It's not specifically related to Earth.
Yep, good. So your little g value, when you look at this equation here, this, purple's not the green color here. Then we take this section of the equation. So we take that section of the equation, and we put in Earth's numbers as Brendan was telling us. Right? That little section of the equation is equal to lowercase g, 9.8. So instead of going through this calculation every time I ask you to find the force of gravity, all right, we just simplified it to g equals the g m, I'll put e here for mass of the Earth, divided by the radius of the Earth. Okay, so lowercase g is the, green doesn't really show up too well at the Brendan. Maddie, can you read that back there? Okay. So your lowercase g, which we call 9.8, is the new gravitational constant that you just learned this morning times the mass of the Earth divided by RE, or the radius of the Earth. Right, so if we want to find the gravitational field strength of Mars, right, we put in the mass of Mars and the radius of Mars, and it works out to be like 3.7. Right, so you can figure out what your field strength is wherever you go. This second little business here, right, so then when I put this, that's kind of left. This little block here, I just put in there to kind of reflect our units, right? So it's your newtons divided by kilograms. So you can see that when we did our equations, right, we always found Fg is equal to m times g. Well, that's really m2 in this equation up here, so that's whatever that second object is. Right, but we never really worried about that because you didn't know about this part here. I'm just kind of like letting you peek behind the curtain here about what gravity is. So little g is a summary. If you wanted to find like what the force of gravity is here in the classroom, right, you can do that pretty easy. You have, again, the mass of the Earth, which we have on our formula page. The only thing you have to do a little research on would be how far we are above sea level, or how far we are away from the center of the Earth. And then I'm sure you can find that pretty quick. I think we're about 350 meters above sea level, so you can add it onto the radius of the Earth, and then you find what the g value is here in Kitchener. Right? At the height of the building, you can see how much it changes because you're on the 3rd floor. It wouldn't be very much. Okay, so that is the difference between the two. Or do you have any questions with that? Does that make sense? The last one here, so that was 4, I guess, my list here. And then 5, when you have your planet or anything with mass, right, what makes gravitational fields different than the other two fields, or one of the things, there's a couple of them. One is that a magnetic or gravitational field only goes towards your object of mass. Right, so Alex kind of said that at the start. Your mass is force of gravity is only an attractive force. You can't use the force of gravity to repel objects. That's just not possible. So remember that in electric fields, right? Electric fields go from away from a positive charge and towards a negative charge. So in gravitational fields, they always point towards the object of mass that's in the question. So the heavier the object, the more field lines it would have because it would be stronger. Any questions with any information on this slide? A fun fact with all of this is that the force of gravity from Jupiter, which we all know is really far away from us at this moment, has a stronger force of gravity acting on you than the person beside you. So when you think about that, right, the distance obviously is not very big from the person beside you, but because Jupiter is so big, right, the biggest planet in our solar system, its force of gravity is bigger on you than the person beside you, which I always think is crazy. You sometimes see in movies, right, where like if people are some event happens when all the planets are aligned, something might happen as part of the storyline, right? Part of that would be the force of gravity stronger on that day. All right, so on this slide here, just kind of a summary between the two fields covered so far, and then we'll come back to this one, we do our 3rd field later in the week. All this is just, like I said, just a very quick summary. Right, so we have our two fields that we know. We know that in terms of our electric fields, right, the electric field is the Greek letter epsilon. Right, just make sure that we can do the shorthand of that too. Right, so our direction of our field, which was on our test last week, but knowledge-wise will be this week. So your direction of your field for an electric field depends on your charge. Right? It's either towards the object or away from the charged object, just depending on what the charge is on that object. In the gravitational field, as we just mentioned, it is always towards the object. So it's always towards the object that creates the field. There's no guessing game there. Right, and you know from the equation that the farther you are away from the object that generates a field, the weaker the force of attraction is. A neat thing to think about sometimes is that there is a point between here and the moon, right, where there's no force of gravity acting on you. Because the force of attraction to the moon is balanced out by the force of attraction to the Earth. So if you were stopped at that point in space, then you would remain motionless between the two planets. But if you differ from one side to the other, on that point, then you'd slowly be attracted to one planet or the other if you're in space. The units for these fields, remember, we just wrote this down too. Units for electric fields were newtons per coulomb, and gravitational fields are newtons per kilogram. So their units are pretty simple compared to what the magnetic field ones are, but we'll talk about that later in the week. And then the symbols are at the top there, right? So epsilon for electric fields, G for gravitational fields. Any questions on that slide? Kind of a quick summary of the two things. So this one here, I put up why this was an important equation. So, like, if you look back at the history of science, why this equation might be more important than others, they're all ranked too. And the reason why this one was important is that it was the first one that was used to predict the motion of planets and stars in the night sky. So before Newton's time, right, astronomers would look through their telescopes, they would plot the position of the stars or the planets and use that to try to make a model, and it's called the heliocentric model of the universe. So when Newton came up with this equation, which kind of ties everything together, he was able to use the equation to predict the motion of stars and then the size of different things, or if he knew the size of something, to predict how it would react. And so that was good for his time, but now the big thing in the news over the last like 10, 15 years is the discovery of planets that orbit stars that are far away from us. So, and by far I mean like a little slice of the Milky Way galaxy. So we're still talking about within our galaxy. Actually, when you look at it on a picture, it's not a very big part of space, but they have found lots of planets that orbit different stars. And all of the information that you would read if you ever read this information about exoplanets, they call it, are all based on this equation where they can figure out based on the speed, the mass of the star, and the mass of the planet, and all this other stuff. And then the other branch that is popular in astronomy at the moment is the study of dark matter and black holes. So dark matter is a type of matter that exists everywhere. It's in the room right now with us, but scientists don't know much about it because there's no way to detect it. So they call it dark matter because it's there mathematically, but there's no technology that can be used to see it or analyze it. But when they look at the motion of stars and things like that, based on visible matter, which is kind of complements dark matter, is things don't follow Newton's laws very well, but so that's where they come up with the idea of dark matter. Is there any video up there that you guys are interested in that you want to watch? I just put a collection up there. I don't know if you find it interesting, I can show you the video, and if you find it boring, I don't always time on it.
Top left.
Top left? Yeah. With the star being black hole?
Yeah.
All right, let's do it. Just a second. No, this one.
Able to do the unthinkable. They allowed humanity to live.
Why it was important, or still is that it described the force of attraction between two objects, not as Newton did that we looked at earlier, where you have two objects of mass and they kind of come together. Einstein's general theory of relativity is based on the concept of like a trampoline. And if you ever look up online, they usually use a sheet or a trampoline. And when you have objects that have mass, just like you standing in the middle of a trampoline, the surface of the trampoline curves in to where your feet are. So Einstein described the surface of everything as the fabric of space-time. So it's one word with a hyphen, space-time. It's a four-dimensional thing that has the three dimensions that you know, and then the fourth one is time. And when you have objects that are large, like you standing on the trampoline, you bend the fabric of space and time, and that causes the different effects that we call gravity. And so you'll see it here in the video. And then the video on the left, I'll show you too, is just Brian Greene. I don't know if you've seen him before, but he's a guy who's on a lot of shows. He's a physicist that speaks well. And I've read a few of his books. So we'll start with this one here. Oh, I need to switch my mics again. So when you're watching this video, I just want you to be able to answer the question, what is the theory of general relativity? And then we can talk about it after the video is done. If needed.
Accelerating up to media. I think you said that it will fall because the gravitational force accelerates toward the ground. But what is the ground accelerating up to media? Suppose I drop an apple. According to Isaac Newton, the ground can be considered at rest. Earth applies a gravitational force to the apple, and that force causes the apple to accelerate downward. But according to Einstein, there is no such thing as a gravitational force. Instead, it's more appropriate to think of the apple as stationary, and the ground, along with everything on the ground, as accelerating upward into the apple. Now, that sounds preposterous and maybe even moronic, but it's not sophistry. There's something substantive here. And today, I'm going to clarify what exactly this point of view means, why Einstein came to adopt it, and how to plant the seeds for what would eventually become general relativity. Ready? Okay, bear with me for a minute, because we need to begin with some Physics 101 and Newton's laws of motion. To analyze motion, you need what's called a frame of reference. That's just some XYZ axes label points in space and a clock to track time. The reason you need a frame of reference is you can only measure motion relative to other things. If that concept is not familiar to you, need to pause me right now and go on this super awesome 1960s black and white video from MIT all about frames of reference. It's amazing, and I promise you won't be disappointed. Welcome back. Now, Newton's laws can't tell you whether a frame of reference is really at rest or really moving at constant velocity, because that distinction is meaningless and simply a matter of point of view. However, interestingly, Newton's laws can tell you whether your frame of reference is really accelerating or not. Here's how that works. Take an object with no forces on it and let go of it. If it stays right where it is, then your frame of reference is not accelerating, and we call it an inertial frame. Now, in Newtonian physics, inertial frames are special because Newton's second law, F equals ma, is only valid in inertial frames. In other words, the net force on an object will equal that object's mass times its acceleration, only if you're measuring that acceleration using an inertial frame. For example, suppose you're in a train car that starts accelerating uniformly forward along a flat track. Relative to the car's interior, you will accelerate backward, even though you can't identify any horizontal forces on it. So inside the train car, F decidedly does not equal ma, and the train car's frame of reference is not inertial. In contrast, a frame attached to the tracks pretty much is inertial. This is just rotation. Because relative to that frame, you don't accelerate at all. Instead, the train car accelerates forward underneath you. Now, more generally, any frame that accelerates relative to an inertial frame will not be inertial. You got that? The inertial frame and non-accelerating frame are synonyms in Newtonian physics. In fact, you can think of inertial frames as the standard against which you measure true acceleration. And for the perspective of inertial frames, motion obeys a simple rule. F equals ma. Alright, let's look at things with the train car's frame of reference, though, a little more carefully. Inside that accelerating train car, not only does everything accelerate backward for no apparent reason, everything accelerates backward together. Fuel and element will all merge toward the back of the car with the same acceleration. Remember, from the preferred point of view, the inertial frame is attached to the tracks. You can book the element are all stationary, and it's only the train car that actually accelerates forward to intercept. So of course you move in lockstep as viewed in the train car's frame. But hold on a second, there's something else familiar that makes people book to elephants accelerate in lockstep. The Newtonian force of gravity. In fact, in the absence of air resistance, that's the defining feature of gravity. So in the train car's frame, which is accelerating forward, it's as if there's an additional gravitational field that points backward. So accelerating frame of reference mimics a gravitational field in the opposite direction of the frame's acceleration. That's interesting. If you combine that extra fake gravitational field with the actual gravitational field here, which points down, it looks like there's a net gravitational field inside the car that points at some angle down and back. Destin, smarter every day, has a pretty famous video of a helium balloon in an accelerating car that happens to illustrate this point really well. Destin generously gives permission to show it, but you should check out the full video by clicking over here or following the link we have down in the description. Now, as you can see, when Destin hits the accelerator, a pendulum hanging from the ceiling tilts back, while the balloon that's tied to the floor tilts forward. Destin explained that air is piling up in the rear of the car and then slightly denser there. So the balloon is just trying to go toward the less dense air near the front. All of that is true. But there's another way to think about this situation. You can also think that the car's forward acceleration is mimicking some extra gravity moving backward. Combine that with Earth's real gravitational field, and it's as though the total gravity inside the car points down and back around a 30-degree angle. That is the new vertical. And the pendulum string and the balloon string are just aligning with the vertical the way they always do. The pendulum aims down, and the balloon aims up, because air is denser on the ground and less dense at higher altitude. In fact, the accelerated frame of reference of Destin's car is completely indistinguishable from having that car stationary on the surface of some other planet with slightly bigger gravity than Earth and tilted upward by about 30 degrees. See what I mean? If you blacked out the windows and put perfect shock absorbers in the minivan, then for all Destin and his kids know, they're completely at rest, tilted upward on another planet in a perfectly inertial frame. Huh. Now, in Newtonian physics, this is just an accounting trick that has no broad significance. Really, Destin's car is accelerating, and this extra backwards gravity is fake. But Einstein asked, hold on, what if the so-called real downward gravity refers is also fake? A science that generated because Earth's surface is really accelerating upward. Now, you know what Newton said. He'd say, that's crazy. He reminds us that inertial frames are standard for measuring true acceleration. So you can only say Earth is really accelerating upward if you can identify an inertial frame relative to which Earth's surface accelerates upward. And there's obviously no inertial frame like that, right? Well, not so fast as Einstein. Maybe there is. What about a frame that's in free fall? Think about it. If I put you in a box and drop you off a cliff, then in the frame of the box, everything just floats, weightless. The falling frame of the box behaves just like a stationary inertial frame that's way out in intergalactic space where there's no gravity. So why can't the box's frame be inertial? Well, because, Newton says, that frame can't be inertial. It's really accelerating downward at 9.8 meters per second squared. The interior just seems like 0 G because the downward acceleration acts like a fake extra upward gravitational field that, from the perspective of the box, just happens to exactly cancel the real downward gravitational field of Earth. My coincidence. Really? Einstein says, look, buddy, I'm just following your rule. You establish the test for what an inertial frame is. Release a force to the object and it stays put. Stationary frames in intergalactic space pass that test, but freely falling frames here on Earth also pass that test if your so-called gravity is fictitious. More to the point, Newton, if you're inside the box, there's no way for you to know that you're not in intergalactic space. This ability to distinguish free fall from lack of gravity has a name by it. Einstein called it the illusion. And if you buy it, then maybe the falling frames really are inertial. If so, then it's the falling frames that establish the standard non-acceleration, in which case it's really ground that's accelerating upward. And what we've always been calling a gravitational force is an artifact of being in an accelerated frame of reference. It's not different from the weird backward jolt that you experience on the train that you know perfectly well isn't being caused by anything. So why are you insisting that the downward jolt we experience every day on Earth has a physical origin? Maybe gravity, just like that backward jolt on the train, is an illusion. But now one seems simpler. And Newton says, nice try, Einstein, but you forgot something. Earth is round. Down isn't really down, it's radially inward. And this creates two problems with thinking about really falling frames as inertial or thinking about gravity as an illusion. First, two objects in a falling box are falling toward Earth on not quite parallel radial spokes. So the perspective inside the box, they won't actually remain stationary. They accelerate toward each other slightly, even though there are no forces on them. It's in violation of F equals ma. Second, now your criterion, Einstein, orbiting frames of reference, like on a space station, should also be considered inertial. Those frames accelerate relative to frames that are just falling straight down. And if you recall at the beginning of the episode, inertial frames aren't supposed to accelerate relative to each other. Huh, that's a good point. So it looks like game over for Einstein, right? Well, not quite. It turns out there's a loophole that makes Einstein's viewpoint self-consistent. The rule that inertial frames can't accelerate relative to each other turns out only to be true if the world has what's called a flat geometry. Instead, the world is a non-Euclidean and curved spacetime. And a straight line at constant speed doesn't mean what you think it means. And it turns out that inertial frames in a curved spacetime can do almost anything they want. It took Einstein about 7 years to realize that. But once he did, a beautiful model of the world emerged called general relativity. It makes several predictions of Newton's theory gravity is not, and so far, it has passed all its experimental tests. And one essential precept of general relativity is that we inhabit a curved spacetime. And in that curved spacetime, the orbit of the ISS is a constant speed straight line. The arc of a basketball during a three-point shot, constant speed straight line. But you, sitting perfectly still in this chair watching this video, you, my friend, are accelerating, giving you the impression that there's a force of gravity when in fact no such thing exists. Wait a minute, how can geometry and straight lines possibly work the way I just said? Patience, grasshopper. We'll tackle that another time. For now, just reflect on Einstein's inspired thinking and how he got there. Maybe next time you get in a car or a train. We'll reconvene next time our accelerated paths cross in curved space. Last week we debunked media coverage of so-called habitable exoplanets like Kepler 186F. Let's dive right into your...
Make sure this other video and then we'll talk.
Welcome back, everybody. My next guest is a professor of physics and mathematics at Columbia University and a co-founder of the World Science Festival. Please welcome Professor Brian Greene. Thank you. How do you like the science movie? Oh man, is that the orbital run? That's the first time I've really science movie. You can rent that for conventions. Tell your science friends. I will rent them all available. All right. Well, you are here not only because you're a fascinating guy to talk to. Thank you for being on my last show.
Oh, I love it. Thank you.
But also, this is the 100th anniversary this month of Einstein presenting his general theory of relativity. All right. I know it's famous. Okay. Why is it epoch-making? Why did it change everything?
So we did not understand how the force of gravity worked before Einstein gave us the general theory.
Did Newton teach us that gravity comes from
That's what you would think. That's what you would think. But actually, what Newton gave us is a formula that tells us the strength of gravity, but he never told us how gravity actually exerts its pull.
Did he not care?
He cared. In fact, in his own writing, he said that it was a critical question that needed to be addressed. But he said, "I will leave it to the consideration of the reader." He couldn't figure it out.
So then Einstein read that and said, I got this one. Yeah. So stand back, guys. Alvy's here. All right. So when does special relativity come out?
1905.
So 1905. That is what you call annus mirabilis.
Yeah, he had 5 fantastic papers. Special relativity is among the most famous, where he redefined our understanding of space and time.
Okay. What does that equal MC squared?
Equals MC squared was an afterthought of the special theory. Yes.
It's like, oh yeah, by the way, yeah, equals MC squared.
That's right.
Yeah.
In June of 1905, he published his special relativity. In September, he has a little extra idea, which is equal to MC squared.
Oh man. Okay. So this is 10 years later.
Yes.
And has he got any hits in between those two?
He published an enormous number of papers, but his real focus, the passion of his life's work, was to figure out gravity.
And how did it come to him that how this works?
Well,
You know, we're gonna form the question.
No, he's deeply puzzled. How does the sun keep the Earth in orbit, right? What is gravity? He's thinking about this, and one day in 1907, he's in the patent office in Bern, Switzerland. That's where he started, right? And he had what he calls the happiest thought of his life.
Wow.
And the thought
Is that something that we can say?
we can definitely talk about. I don't know your happiest thought, but his we can talk about, right? So he imagines a man falling from the roof of a house.
Happy.
And he realizes that man would not feel his own weight. He would feel weightless.
As if he falls.
He's on a scale, right? The scale's going to drop to zero because he's no longer pushing on the scale. He's falling with it.
I understand this experiment to demonstrate that.
Yeah, little simple demonstration. So happy.
Yeah. Okay. Do I do anything?
No, it's very simple, right? So all we have here is a bottle of water that has holes in it, right? So of course the water is spraying out of the holes because gravity is pulling on the water, right? But Einstein is right. If I drop this bottle, the water will no longer feel gravity, so the water should stop spraying out. Let's see it. 3, 2, 1.
Whoa. Come on, okay. Now, did Einstein have any theories about who's going to think that up, right? Okay, so he saw that, he thought of that, and then general relativity.
8 years in the mind of Albert Einstein.
So he thinks about it for 8 years. What's next?
Yeah, so then he realizes that there's a link between gravity and motion.
Yeah,
And using that link, he comes up with this idea for how gravity works. So this is meant to be the fabric of space, okay?
Okay,
He
flat,
says-
flat,
It's
okay.
flat, right, exactly. So he says that there's no matter in space is flat, right? Which means that if you roll something, say a planet is moving through space, it goes in a straight line,
Okay.
But now let's bring in the sun, right? This is the sun right here. And he says, in the general theory of relativity, that the sun, merely by virtue of being in space, warps the fabric of space, actually, and time, okay? And that's
Like,
vital.
it makes like a well.
A well, in a sense, because now if you take the Earth, right, and we set it in motion, it now goes into orbit because the fabric of space is nudging it around. And that, according to Einstein, is how gravity works, right? So we get these guys moving, all of these planets, objects, like they just do something off the edge of the universe. Right? So this, according to Einstein, is how the force of gravity actually works. Put some, let's say, asteroid in there, and let these guys go in motion. Go crazy, go crazy.
Wait,
There you
in
go.
direction, or?
Oh, it's up to you, man. Go nuts, right? There.
I think I've turned the fabric of space-time.
And then we have some of these guys over here.
Wow. Oh, and those planets are on fire?
There they are.
I got one more question for you. Everybody always says, this is a beautiful demonstration. Everyone always says to guys like you, can you dumb it down to the level of like a 5-year-old? I would like you to not dumb it down. I would like you to say it to me as if I were my age, 51, but had an advanced degree in physics and high mathematics. Give it to me in less than 30 seconds, but let me just lean into my ignorance of what you're saying to me.
So Albert Einstein says that space-time is a four-dimensional Hausdorff differential manifold on which a metric tensor is imposed that solves the Einstein field equation, and that metric tensor gives rise to geodesics, and objects that are not experiencing any other force will move along the geodesics described by that metric.
Okay, so out of all that, what did you guys get out of those videos there? What did you get? Anything out of the videos there? Let's see. Okay, okay.
So which idea are we supposed to be looking at? The Cambrian idea or the idea that it's being pulled in one direction?
Well, they're both. Both are true.
Both are true.
Both are true. It depends on how you're attacking the question. So all the math we do in our class based on Newton, we're doing, because the math we're doing is Newton. That's what you have the skill set to do in high school. If you were to go on further in some sort of weird or different physics field where gravity is an issue, then you'd fall under more of the relativity aspects.
So the theory of relativity is like actually how the universe works, or just like
They both work together. Like you can use Newton's laws to predict the motion of planets around the sun or satellites or distant moons around different planets. So it is also how the world actually works. So it's not that it's wrong, or if you learn this and learn the general relativity later that you wasted your time learning this. It's not. There are two ways to describe how things work. The problem with Newton's laws is that it doesn't explain how light interacts with gravitational fields.
and this one does.
And this one does, right? So in the video we watched about dark matter, when the narrator Damien was talking about like gravitational lensing and things like that, it's based on general relativity. And when Einstein was doing his thing about general relativity in 2019, what did they say, 1915? I forget what the year was.
100 years ago.
Yeah, but when he was doing that, the only way that he could prove his theory of general relativity was to look at a solar eclipse. Because if you could look at a solar eclipse, like a perfect one, then in the idea of gravitational lensing is that if you have your the gravity refracts light. So this is my sun, and there's a star back here, and it's the perfect, that's Earth, perfect solar eclipse, right? That moves between the Earth and the sun, right? It blocks out the sun. So to prove general relativity, Einstein had to go to a certain part of the world where this was happening, because the light from the sun, or light from a distant star would go around the sun and then refract to the Earth, just like a lens would refract light. And what he was looking for was something that looks like this, but then you'd see it twice because the light from the other side would also refract, just like lenses on on glasses. So this is not explained by Newton's laws of physics, but it is explained by general relativity. The problem with his theory, or the developmental part of it, is that when he came up with this idea and wanted to prove it, he set up this experiments, I forget, somewhere in Africa, and then World War I broke out, so then he couldn't actually go do it. So he had to wait for another time. I think it was in the 30s or something like that, and then World War II broke out, so then he couldn't go there either. So it was much bad luck. And then eventually it was proven that gravitational lensing does work and general relativity is true. Does that answer your question?
My question was, which one do we think of it? You have to do it, right? So,
Okay. Yeah, we think of gravity, for the most part, everything that we do in our class is about math and things with math, which Newton's laws work with. When you get away from math and fields like that, it's more relativity based. But it's not until you get really high level math skills you actually dive into the stuff. Yeah. Right? So, not many people do. I remember my third year class in university 20 years ago where there's the three of us and my professor was one of 7 people in the world that could solve this equation going through this math. And it wasn't fun. That was a long time ago. So overall general relativity, what you need to know, the highlights is that it's based on the fabric of space and time, right? It talks about how things that have a large mass can warp this fabric of space and time. We haven't talked about special relativity yet, right? That came out first, and that's what we're going to talk about on Friday. But when you get into general relativity, when these massive objects bend this fabric of space and time, it also changes what you think as length and distance and time. And I'm sure you've seen some sort of movie that relates to black holes or space, and if you haven't, we'll talk about it on Friday, about how when you get near objects that are really heavy, then time slows down, crazy weird things happen. All right, so that's what general relativity is, right? It's just a different way of looking at gravity, obviously a more complex version that we need to know. What did I hit there? Okay. So this is the final thing here. Then there's math. So we'll take a break and we'll do math. For gravitational waves, we're in the news a little while ago. You can watch these videos here too. It was a big thing because it proved general relativity is not proof for it. So based on the fabric of space and time, the idea was that if a big event happens in space far away, the ripples like water ripples on a lake, you should be able to measure that change in gravitational field because the space-time will ripple through the universe. And it's something that happened about 5 years ago where they were able to measure the gravitational wave due to something that happened far away in space. So that was pretty cool. And if you're interested in that, you can watch one of the videos there. And then you guys kind of know this. Yeah. That the Earth is not a perfect sphere, so the force of gravity does change where you are, depending on where you are on Earth. And I mentioned this before, but the Earth, right, is fatter at the equator, and then it is at the poles. So if you look at where countries have their space programs, when they launch satellites in space, you'll always find that their space programs are launching areas are the nearest they can get to the equator in their territory because the force of gravity is less in that space. Right? In the United States, their launch sites are in Florida and Texas because the gravity is less there than it is in Buffalo or Boston or Seattle, which is or Alaska. Because they're closer to the center of the Earth. Russia's the same, right? They're in the old USSR countries, which are closer to the equator and far away from where Moscow is. Same idea. As you go into the Earth, too, there is a spot where you go into the Earth, and then once you hit that spot, the gravity decreases, and then if you were in the core of the Earth, right, there's equal mass all around you, so there'd be no gravity technically because everything would balance out. And then the last set of questions here, which you're going to see this in your homework questions about satellites, because that's part of what we talk about. One is called a geosynchronous satellite. So I don't know if you've heard that term before, so I put it on the slideshow. A geosynchronous satellite it orbits around the equator, and it orbits at the same speed that the Earth spins underneath it. So it's stationary above a certain point on the globe. So all of our telecommunication satellites that we use, like our cell phones or TV, all that stuff, they're all attached to geosynchronous satellites that orbit around the equator, but are obviously directed out at Ontario for us. So we always get that signal. Right? If the satellite's not around the equator, or it's going faster or slower than the Earth spins, then it's not called geosynchronous. It actually looks stationary. So the image on the bottom right would be what the satellite sees. You can see that it's always over top of the same spot on the Earth. Right? You can see the day and night going across the globe there, but the image underneath it never changes. Right? You can see where is it? There's Mexico, right? Florida. So it's right over top of the Earth there, but it's orbiting around in space just like the moon goes around the sun. The big thing here, terminology-wise, is when you see the word geosynchronous in question, it's about the Earth's period. So the period of rotation is 1 Earth day, so you have to just convert that to seconds. Right? Because the Earth goes around once a day. If the satellite was not at the equator and had the same period of Earth, it still would not be a geosynchronous satellite because you can't park a satellite that focuses just like straight above Kitchener because the Earth it can't work that way. That would have to orbit around this way around the Earth. It would keep the same distance around the surface of the Earth. So if you ever, there's spy movies that you can watch that they sometimes look for satellite images of whatever, right? And those satellite images, sometimes they talk about a window where they can take the pictures because the satellites, they're trying to take a picture of, like, say, Kitchener. The satellite would come over top of Kitchener briefly, and you could take your images, but then would fly off and continue its orbit around the planet. right? If you look at Google Earth, right, or Google Maps, right, from satellite view, you'll see that it's like blocked, so you can see the path of the satellite across the Earth that took the pictures. If you zoom out far enough, and there are different seasons sometimes of different pictures, so you can see the track and how the satellite went over the area. The last slide here, there's just a difference between natural and artificial satellites. So they're just words that are going to pop up in your textbook. Natural means, well, nature. I don't know if you have to write that down, right? Natural satellites would be like the moons or planets. It refers to objects that orbit other planets. So planets orbit a star, they're not called satellites, they're planets. And then satellites are objects that orbit planets. So I put a picture of my favorite moon up there. I don't know if you guys have a favorite moon. Probably not, but I do. Mine's called the Death Star moon. It orbits Saturn, and it was discovered after Star Wars was created. And you can see how this moon looks like the Death Star in Star Wars. It's called the Death Star moon. It has a huge meteor impact there that caused that, which would have been a satellite dish. But you have Titan, which goes around Saturn as well, and then different moons that go around Jupiter, where NASA is looking for life, and they're actually sending one out to one moon called Europa over here. So there's a little video there that you can watch on your own, or you can watch it later too. So artificial satellites are man-made things that orbit different planets. So it could orbit our planet, or it could be an explorer that orbits other planets like Mars or Jupiter. Those are all called artificial satellites. Okay. Last but not least, I put this up here if you're interested. We're going to take a break so watching videos. But these are just different videos. I don't know if you've seen them before. This one's what it's like to be in zero G. There's a plane that they have in Europe called the Vomit Comet. And what it does is it goes up and down like this as it flies through space. So when it goes down, it can change its tilt to simulate the force of gravity on different planets. So if it goes at a steep enough dive, then the people inside the plane are in free fall. So it's like being in space. They use it to train astronauts. I know there was a Bell commercial that had it too, where they filmed it on there. The person that was, I think, paraplegic, and then they can move around in space freely, right, without being in a wheelchair. And then there's one with Chris Hadfield, my favorite astronaut, talking about kind of the effects of being in a microgravity environment. It shows how he works out, or he worked out when he was on the space station. And then these other videos about how satellites get in orbit and how GPS systems work. All good topics for your presentation or your papers for this unit if you haven't chosen one yet. And we're going for a break, and then when we come back, we'll do our math. It's going to be dropping objects in the form. And I don't have a great way to measure the time it takes for an object to fall in the form. So if you, in your experience in life, you can figure out a way to calculate the time it takes for an object to fall. You don't tell me now if you guys have any idea.
Count 1, 2.
So we can be a little more accurate than counting with our fingers.
With their phone.
That's what I mean. Like, I don't know how, if you guys can think of a way to use your phones to do like more than counting 1, 2, 3, 4.
No, you just like press the timer when you release it.
Yep.
And then when you hit the ground, you hit it again.
Sure, but then there's a reaction time.
You just subtract the reaction time.
You could, right? So then we have to measure your reaction time, which is a fun thing to do. Have you guys ever measured your reaction time before? You guys know how to measure reaction time?
Is it like the ruler?
Yeah, the ruler trick. Do you guys ever do that?
There's websites where you can do it.
You can do that too. Yeah. I feel like we should do that. Maybe we'll do that tomorrow. We'll measure our reaction time. It's a fun activity. Okay, so let's do this. So anyways, going back to my original question, if you can think of any way to use your phone to accurately measure the time of falling objects more, that'd be great. They used to have a good app, it's called Coach's Eye, where you take something that it went down to milliseconds, and you could like slow motion, fast forward, and slow it down to. It was meant to, like, if you're watching a hockey player shoot, you can watch the mechanics of the shot and break it down to the athlete. But it used to be free, and it's not anymore, so you guys don't have that option. But it's something like that, where you can measure frame by frame how long it takes something to happen. If we look at this example problem, so we're going to do, I have 3 different types of problems. We're only going to do 2 of them, because the third one is something that pops up in your homework. It's more of to prove a point than to actually do the math. Andre?
So you can probably just use slow-mo on your camera.
Does that do time too, though?
I wasn't sure of the time aspect.
We need the time. Yeah, I know. Like, I've used slow-mo to take videos before, but it doesn't have like a time.
It's not very accurate. It's like 1 second, 2 seconds.
Yeah, right? So we're like, if we get a millisecond accuracy, then we're doing better than counting with our fingers.
Yeah,
Right? So we take a look at this question. It's a pretty typical question. We're going to find the gravitational field strength of Saturn. So I'll just pick a planet. And here, I gave you the stats of Saturn. You don't need to memorize that because that would just be crazy. There's no diagram needed for this either, if you don't want to, but we're just doing a pretty straightforward calculation. To do this question, we have, we're going to start with our equation that we started with today. So we have the mass of Saturn times, I just call it M2, because it's like whatever else you want to be. G, and then RS is for the radius of Saturn. Okay? So if you need to note that, you can. When we talk about gravitational field strength, so the wording, right, gravitational field strength here, we have Fg over M2 is equal to, what's left, G, ms over r s squared. Because your field strength, remember, is always in force per kilogram. So that's why it's Fg over M2. M2 could be anything. And then we know all the stacks that are on the right side, so we just run our calculators to get the right answer. We have the G, again, 6.67 times 10 to the negative 11 newtons times meters squared over kilogram squared. We have the mass of Saturn, which is 5.69 times 10 to the 26 kilograms, divided by the radius squared. And everything works out well here. Type in your calculator, it'll make sure you get 10.4. Because when you look at that, it looks really weird that it works out to be a quantifiable number, not weird like exponents, it's just 10.4. Right, so double check, make sure you use the exponent key correctly, all that other stuff. All right, that's like our mild type question, right? Just plug and play. The questions never differ, right? If you see the question gravitational field strength, that's what it is. Okay, so that's the easy one, a softball question. Now we're going to go into the harder one. So next slide here. Good. Okay, so this is a geosynchronous question. Or actually, it's not, it's just something. Again, this is a pretty typical question. There isn't much variety in these types of questions, unlike our other units. You can read the question as well as I can, and we will work through this together to get the answer. This is a combination, though, just to give you a heads up. This is a uniform circular motion problem because we're dealing with something important. So we're going to be going back to our knowledge of that, kind of tying it all together. So in this case here, we will do a diagram. So we have our planet Earth, we have the International Space Station somewhere above the Earth, and we have our A. So A stands for altitude, which is 350 kilometers. Right? Yep. So A, actually it's not a vector. You can use whatever letter you want here, but usually when you see in the textbook, they use A for altitude instead of H for height. Right? Altitude just means how far you are above the Earth's surface. And we also have the radius of the Earth. So we have RE. And when you put the two together, that's our R value. So our R is going to be RE plus K. All right, so anytime you get an orbital question, you... it has the same setup. So, that's a check. Okay, all right. Are we good so far? Okay, any idea what the free body diagram is of the International Space Station? Pretty simple one. Okay.
Force of gravity.
Yep. My free body diagram is a little weird because I didn't draw my satellite right above, which would make it easier to do. All right. So my force of gravity goes towards the center of the Earth, whatever it would be, and that is the free body diagram. That's it. Okay. The reason why that's important is that when we do our next part, which is which concept do we use to solve this problem? With everything that we do, right? Conservation of momentum, conservation of energy, Newton's laws of motion, projectile motion. Which theory or concept are we going to use to solve this problem? Any ideas? We're dealing with the motion of an object that's in a circle. So which theory works with the motion of an object in a circle? Well, which one?
It's the second one.
Good. So we're going to use Newton's second law of motion. So we have F net, right, equals MAC, right, for centrifugal motion or circular motion. Right, if you want to, you could draw the orbit of a satellite going around the Earth if it makes you helps you understand it better, right? Just so you know it's going in circular motion. Okay. We know from our free body diagram we only have one force, the force of gravity, and we still have MAC over here. So again, our net force equation is not very spectacular, right? One thing we should put in here, we're talking about the International Space Station. So we put S. So just to remind you that MS is the mass of the space station. That's what that's moving here, not the Earth. All right, our equation that we started off with today, we have G, M of the Earth, M of the space station, divided by R squared, is equal to MS. And what equation are we going to use for the centripetal acceleration? We have three options, remember, Jackson?
Equals V squared over R.
No, not in this case. We're not going to find speed that has an orbit around the Earth. Ashley? Yeah, which one's that? Yeah, perfect. So we're going to use the equation that has time in it, because that's what the question's asking us. So, Jackson's, you could still do your route, but it takes more steps. So it's not wrong. You have to find the circumference of the Earth and then get the final answer. Just more work. So in this case here, we're trying to find T. So how do we find T here? At the end of the day, we want T equals something. It's going to be the square root of something. What is T equal to? So a lot of people writing stuff down. What is T equal to? I don't know what T equal to.
I have 4 pi squared over G mass of the Earth.
sorry, 4 pi
4 pi
squared.
square over gravitational constant times mass of the Earth.
Nope. Missing something. And?
4 pi squared r cubed over g and
Yeah, good. So the MS's cancel out, right? There's one on each side on the top. So we can cancel these guys out here. Right? The r squared has to come up to the other side. So we have r squared times r over here. So that makes it r cubed. So the 4 pi squared, now becomes r cubed. And then we have to bring the g and the me across, and they come underneath here. G, M, E. So if you would have to find the radius here, just be aware that you would have to find the cubic root of whatever is there. Just the only time this year we've done that. So now you can throw in the numbers that we have as a heads up or just caution. I'm going to switch over to chalk here. Right, we have t is equal to, let's move my camera over. We have 4. What do we use for r? What do you guys put down for r that are typing things in your calculators? Ashley? Yeah. So you said 6.37 times 10 to the power 6 meters? That's it? Yeah. So you gotta make sure you add the altitude to it too, right? So you have, your form sheet have 7 or 8? Right, so you gotta make sure you put your altitude in meters, not in kilometers, right? So you're gonna multiply 350 by 1,000. So that puts it into 3.5 times 10 to the power 5. Right, you gotta cube it, follow the steps. And it works out to be about 92 minutes. You can do it right. What do you guys get for the period? What do you guys get? Alex, what do you get?
Me?
Yep.
I've been following along, I'll be honest.
Where?
I've been following along.
Maybe you check the number you got there?
I just trying to grasp the rearranging.
What part of it do you struggle with? We can talk about that if you want.
I'll be honest, I'm just bad at rearranging with the divided.
Okay, so what I would do is, here's mine. What I do, because I hate fractions, is I always cross multiply first. So the MS is still cancel out, but on one side I'm going to have g me times t squared is equal to 4 pi squared r cubed. Does that make sense to you?
Yeah.
All right, so it's just a cross multiplication. And then, so for all of these questions, you'll get to the same spot. And then just, we're trying to find t this time, right? So if you divide each side by the g me, right, that's g me over there. Right, and I cancel that, get rid of that. And it takes square root of it. Right, that makes sense.
How do you get 90 minutes?
Isn't it 90 minutes? I don't know what.
I got like 500.
Well, that's not the right answer.
No, that's seconds.
Yeah, the answer you're going to get is in seconds, right?
Just measures.
What do you guys get as your? Is it 55,480?
Yeah.
Yeah. Right? So, I remember when I read Chris Hadfield's book, that was one thing he liked about being in orbit is that they saw sunrise and sunset every 91 minutes. They go around for that fast. So again, trying to calculate it's like probably the hardest thing to type in your calculator all year. There's so many different things in there. You got lots of scientific notation. You have a cube, which we've never dealt with before. So you have a lot there. The last bit here. I put this up here. Whether you want, I won't ask you a test question like this. So do it with it when you like. If you enjoy doing math and vectors, you want to do it. I put this up here just to emphasize the fact that the universal law of gravitation is math-wise is done the same way as Coulomb's law. So again, you have 3 things of mass. And you can find the net force acting on the different charges using the same math that we did before with Coulomb's law. Where if you're doing a straight line one, you find the force of attraction between A and B, and B and C, and then add them or subtract them because they're in different directions. And then that's how you get your answer there. Here, obviously, it's a 2-dimensional one. Whether you want to do that or not, it's up to you. So that's on the slideshow. And then I put these questions on here for you for homework. So these are the textbook questions based on today. I put a question on here, like the one we just did on the board. That's not, I didn't find a good example in your textbook. So that's there. And then just some terminology questions down here. They relate to the application questions I'm going to ask you on your test. So obviously class is almost over. So tomorrow we're going to do our lab, which will be the first half of class. And then depending on how we go, we can spend more time doing homework tomorrow for the second half, and then do magnetic fields on Wednesday. Just quick.